I believe when we get to year 2100, half of all energy in the entire world will come from thorium. And today we get no energy from thorium anywhere in the world. 0.9 cent per kilowatt hour. Lower cost than any other technology on this planet, including wind and solar or fusion.
With our type of reactors, you can run them as breeders. So when you stop one reactor, you can start a new one on the same salt. It's probably more valuable than gold.
All the rules that we knew for the last 50 years are sort of suddenly out with the bathwater, because now any small country can make half of all the steel in the whole world. It's a lower risk than most other nuclear startup companies, and much, much lower risk than any other fusion company, because Copenhagen Atomics is actually already generating revenue from the things we do today.
What is more exciting than that?
So, welcome to this podcast. It's all about Copenhagen Atomics. We are today Aslak Stubsgaard, our CTO and one of the co-founders, and myself, I'm so Thomas Jan Pedersen, a co-founder, right now CEO of the company. So today we were going to talk about what is the current progress in Copenhagen Atomics and what are sort of the long-term goals. We will talk about a little bit different things. Maybe, Aslak, you can start and say a little bit about what you find super exciting about thorium energy and molten salt reactors.
Sure. Yeah. What is really exciting about molten salt reactors, and specifically molten salt reactors using thorium, is that you have the possibility of making a breeder reactor that can scale to meet global energy demand at a very low price. And what is more exciting than that?
Yeah. So how far are we towards that goal in sort of a one-liner, if you are able to do that?
Yeah. So we've been working at this for over 10 years now, and developing all the basic technologies that needs to go into a molten salt reactor, because when we started, there wasn't any technologies off the shelf. And we're now at a stage where we actually are building non-fission prototypes and are getting ready to make a test reactor that we can run within a few years.
Perfect. And I think we should clarify also for the audience that the whole idea of using thorium as a fuel and the idea of using a molten salt reactor is something that was discovered back in the 1940s and 50s. One of the main guys behind it was called Alvin Weinberg. He came up with the idea of the molten salt reactor, but of course many other people contributed. And they actually did build one back in the 1960s, or they built a few prototypes, but there was one important reactor called the molten salt reactor experiment that ran for 5 years in the 1960s in the USA. And of course, when we were young and saw that, it was like, why are they not using that? Why did it stop back then? And maybe you can say a little bit about why it didn't completely stop, but why it slowed down, and then why it has increased in speed again now.
Yeah, so there could be many reasons, and many have been hypothesized. But one of the main ones was just that in that era, so the 70s, a lot of funding for public projects like the space program, nuclear reactors was decreased dramatically. And molten salt reactors was one of those technologies that was decided to not continue. But it wasn't forgotten. People still made research on it, but at a vastly lower amount. But still, all this is enough that when we started looking at it, there was a plethora of documents and technology that has been developed that we could build on.
Yeah, and for me personally, that's very important. If there had not already been an experiment that showed that this technology would likely work, and if there had not been all these documents on the internet about how it worked and what tests they did back in the 60s, 50s, 60s, and a little bit into the 70s, I would probably have thought it was too high risk to start a startup company, especially in Denmark, trying to do this. But can you explain a little bit? So all the other reactors in the world, more or less, are solid fuel reactors. And what is the sort of the main difference between molten salt reactors and solid fuel reactors, and why is that important?
Yeah, so the obvious is in the name. So we have a liquid fuel as opposed to a solid. And that means that the fission products that are created as part of the fission process are collected in the matrix of the material. In a solid reactor, it stays in that form. In a liquid, they can be readily removed. And so one of the primary benefits of a molten salt reactor is that you can remove the fission product from the reactor while it's running. You also have other benefits. You can make the reactor more stable in terms of operation. You can have a higher temperature out of the reactor that increases efficiency. But the primary benefit is really that you can remove fission products, which allows you to make a very efficient breeder reactor.
Yeah, and of course I agree that's That's the key here. But maybe we should explain to people sort of why thorium, because you can also run molten salt reactors with uranium, and can you also run solid fuel reactors with thorium, and why is this combination so important?
Yeah, so you can put thorium in a solid fuel reactor, and it can have benefits in performance, but it's a minor benefit because you still have those fission products trapped in the matrix. And what really makes thorium unique is that you can do this breeding process where you produce more fuel than you consume in thermal spectrum, but the margins are not very high. So in a light water reactor where you moderate the neutrons, the benefit of adding thorium is very, very small. But if you go to a molten salt reactor where you can remove the fission products, then this unlocks the possibility of doing a breeder reactor in thermal spectrum, which is otherwise only possible with uranium in fast spectrum. But thermal spectrum reactors just have a lot of benefits compared to fast reactors.
Yeah, thank you for that explanation. I hope the audience can follow. It's a little bit technical nuclear engineering jargon. I'll try to convert it into some simple terms. So it basically means the efficiency of the reactor. How much do you need to pay for the fuel for each megawatt hour of energy you get out? And sort of thorium is very inexpensive, and also the way we can use in molten salt reactors is super efficient. And then, of course, compared to normal reactors that most of the countries in the world have, there's 31 countries that have uranium-based reactors based on solid fuel. And the price difference of the fuel is about 1,000 times higher for the uranium-based solid fuel reactors than for a thorium-based molten salt reactor. So, it's not a small. Normally in industry, we see that if somebody invents something, then it's twice as fast or twice as good or something, or maybe sometimes it's five times better than the technology that was there before. But in this case, it's at least 1,000 times better. And I think also we should highlight when we talk about this that there's this other fuel that a lot of people talk about on the internet called HALEU, which is a type of enriched fuel that has a higher enrichment than the normal fuel used in nuclear reactors. In many cases, it's around 20% enriched uranium. And that type of fuel is even more expensive. So several thousand times more expensive than thorium fuel when you calculate it per kilowatt hour, megawatt hour. And that's, of course, super important because this is the raw cost of the fuel. So no matter how cheap they can make the reactor, they still have to pay several thousand times more for the fuel. And I think this kind of gives people an idea of the scale of the difference here. Okay, so in the beginning you mentioned that Copenhagen Atomics has been working on this technology for more than 10 years now. What are some of the results from this early technology research?
Yeah, so we have had to develop many areas of the reactor, but some of the key areas has been our pump development. So we've built a canned rotor pump that can operate inside of a molten salt environment, inside of a reactor for years at a time without needing maintenance, which has been a huge development. And we now have pumps that we've ran for over 2 years, and we have a combined 100,000 hours of pump time in molten salt. Another big development has been our purification of molten salts. So we have scaled this from when we started in just small crucibles in a glove box up to now it's ton scale, so 1 cubic meter tanks of salt that we're purifying in one go. Another one has been the reactor design itself. So the way we manufacture the reactor, the shape and the form factor and the materials, so that we have a technology that can both provide very low cost of energy, but can also be mass manufactured.
Yeah. So if we look around the world, who else is doing stuff? I mean, there's other people also building pumps, and we have built 120 pumps so far. But so all the other people in the entire world, how many pumps have they built? Is it 10 or 20 or 50 or 100 or?
So we don't have that answer. Of course, they built pumps for molten salts in the 50s and 60s for the reactor tests that were done there. Besides that, people have built pumps for concentrated solar power, but those are operating with nitrate salt at lower temperatures, and they don't need highly purified salts. So it's a bit of a different environment. So there are people out there working on it, but we don't know how many are built, but it's probably not 120.
No, so our assumption is that the rest of the world has built less high temperature molten salt pumps than we have, and we've done a lot of testing. So we're definitely leading the global research in pump molten salt loops. So what about corrosion? What are some of the achievements on that?
Yeah, so for the salts that we use, if you just take them from suppliers and buy high purity salts, they still come with moisture and oxygen in that salt. And so if you just melt that and pump that around, you will get corrosion. Those impurities will basically drive a lot of initial corrosion in the salts. So what we found is that if you remove those impurities to a very low level, you can really diminish the amount of corrosion. And we've done multiple studies, and we've also published a paper in collaboration with University of Liverpool on the corrosion of these salts. Even when it's thorium and uranium salts, in static conditions, the corrosion is very low. We're continuing to do more tests on flowing systems and on heat exchangers and other components to see if this result still counts for a reactor environment. But in general, we're very positive we can actually use low-cost stainless steel materials with highly purified salts.
Yeah, I think this is another important point, because a lot of times on the internet, you read stories that are not entirely true. I mean, there's a lot of rumors on the internet about how corrosive these salts are, and it's true they can be corrosive, but we've found a way to reduce that. And a lot of times on the internet, it also says that you have to use super expensive materials, and it's difficult to make these reactors, and they can never be, not never, but they say sometimes it will take many decades before it works. But because we were able to purify the salt, we can just use regular stainless steel, which is sort of a 10 to 20 times lower cost than some of these other materials that have been proposed for molten salt reactors. So there's significant savings on the building material or the stainless steel.
It's also important to say that classical reactors, the reactor vessels are built to run for 50, 60 years. And people might have that mindset that the reactor vessel has to run with molten salt for 50, 60 years. But our type of reactor, each vessel only runs for 5 years. And then we change out the reactor vessel and we have the salt is continuously purified. So it's not the same structural materials that are exposed for salt for 50, 60 years. They're exposed for up to 5 years.
Yeah, so we actually believe already now what we have today and what we've already run, like you said, 100,000 hours of testing. This is good enough for a commercial reactor. Of course, there's still some other components that needs testing, but the material and the corrosion problem has been solved so far.
Yeah, and in a commercial reactor or even just any high power reactor, you do have other environments that is hard to test in the lab. So you of course have flowing salts, fuel salts, and you have the high radiation environment. And so there are still surprises that could come, but we do have data from the reactors that ran in Oak Ridge in the 60s where they didn't see any kind of severe corrosion from turning the reactor on. In some cases, it actually looked like it was slightly less corrosion because you have this effect that some of the fission products are noble metals. So in the salt, you're creating platinum and like tungsten and all kinds of elements that tend to plate out onto the core structures and sort of gives a little bit of coating. But that's something we'll have to see first in test reactors and then going to commercial reactors.
Let's jump to the next thing I would like to talk about. So we are now roughly 70 people at our R&D facility here in Copenhagen, and we are planning to expand the company this year. Let's talk a little bit about what are some of the people we need to expand the company in the next maybe 1 or 2 years. I know it's a little bit difficult to see 2 years ahead, but let's try anyways.
Yeah, so in general in the company, it's a lot of engineering. It's a lot of welders, marine engineers, and a lot of building and testing. So most of the people that we have now and that we need in the future are people who are hands-on and can build things and design things. We also have people who do license documentation and reactor design and design of different systems. So we have a pretty wide variety. We also have people who do software and electronics. So we sort of span the full gamut of different disciplines. But yeah, we need more of all these disciplines as we scale.
Yeah, so it's probably, I don't know, 60, 70% of the people we're going to hire is going to be with a very technical background. So both different types of engineers and people who know how to run machines and debug machines and keep them running and fix them and so on. But also welders and technicians and electricians and machinists and people with those kinds of backgrounds. We will also need more commercial people. because now we are starting to talk more and more with customers that wants to buy reactors. And so there's one part of that is a sort of commercial discussion about what is the reactor cost and, when can we get it delivered. And we will get back to that later in our discussion. But another part of that is also to help people understand how do they actually get the licenses to deploy these reactors from their local authorities. And we will also help them do that. So that's also sort of a new set of people that we're going to hire, which we didn't have very many of before.
Yeah, and if people are interested in some of these jobs that we're talking about, they can go and apply on our website or look at the open positions. And they can also subscribe to our newsletter to be updated on what positions are coming up in the future.
Let's talk a little bit about the price and business model of Copenhagen Atomics, because it's a little bit different from most other nuclear reactor companies, and later we will talk about how we compare to some of the other ones. But right off the bat, I'll say we're probably one of the only or very few companies who have the price of our nuclear reactors on the website, because most other companies just talk about their team or some other stories, but they never say what the price is of their reactors. But because we have a very low price, we like to brag about it, and that's why we put it on the website. And we're willing to sign contracts already today on that price for people to get nuclear energy in the future.
Yeah.
But maybe you can talk a little bit about how that works. What is the price?
Yeah. So Copenhagen Atomics, we actually, I want to flip that around and say to you, like, what is that price then?
So each reactor unit generates 100 megawatts of thermal energy. And to get started in buying one of those units, it's $50 million, not $50 billion, but $50 million as an upfront payment 2 years before the first unit is delivered. And then it's $2 million per year to keep that unit running for as long as you want. And Copenhagen Atomics will keep on supplying new fuel and new parts that needs to be replaced. Essentially, the reactor unit needs to be replaced, you said, every 5 years before. So that's included in that price. So if you sign up for this contract and you want to run one unit for 50 years, that's $50 million up front, and then $2 million every year for 50 years. So that's $100 million. So in total, $150 million to run one unit for 50 years. And of course, that's not enough to get a power plant. That's just what you pay Copenhagen Atomics. On top of that, the customer needs to buy the land, get some licenses from their local government. They need to build buildings, hire people, build steam turbines, and connect to the grid and whatnot. So those other things that the power plant owner needs to pay for is more expensive than the cost of the reactor contract with Copenhagen Atomics. So it will vary. Some countries it will be low cost, in other countries it will be expensive, and maybe some power plant owners are better at optimizing the price than others. So it's a little bit difficult to predict the price, but we think that the price will be in the range of $29 to $39 per megawatt hour.
So for this cost, they get a reactor and they get the fuel moderator, and Copenhagen Atomics operates the reactor. Is there anything else besides the building that the customer has to provide, steam turbine?
Yeah, the customer needs to provide the entire nuclear power plant with all the buildings and license and all the employees, everything. What we provide is the reactor unit itself and the fuel. And of course, that's super important. And the cost, now I just mentioned before, if you look at it for 50 years, it's $150 million US dollars. But if you divide that into what is the cost per megawatt hour, because that's usually how people compare, then it's $9 US per megawatt hour, or some people like to have it in kilowatt hours, and then it's 0.9 cent per kilowatt hour. So lower cost than any other technology on this planet, including wind and solar or fusion or...
Yeah, so that's even a little bit lower than the cost of just the fuel for a light water reactor per megawatt hour.
Yes, correct. You cannot buy the fuel itself for a light water reactor. I mean, forget about the whole price of the reactor and everything else, but you cannot even buy the fuel for that price for other types of reactors. So it's definitely a game changer.
Yeah. And then what is it that makes it that we can provide this price when light water reactors can't?
So it's basically two things. So first of all, we mentioned before that the fuel for these type of reactors, because it's thorium and because it's a molten salt reactor, so it uses the fuel more efficiently. So the cost of the fuel per megawatt hour is sort of roughly 1,000 times lower than the light water reactor. But then also the rest of it, the size of the reactor is smaller. So that means we use less material than a light water reactor. The pressure is much lower. That also means we need less expensive materials than a light water reactor. So essentially, many things are less expensive. But of course, the R&D cost to get to this point is expensive. So that's why it's not, in the end, the electricity is not 1,000 times cheaper. It's a sort of 10 times cheaper than from light water reactors.
Yeah, and you said that from upfront payment to delivery was 2 years.
Yes.
But when are we then ready to deliver the first commercial reactors?
So we could deliver commercial reactors in a couple of years from now, 2 to 3 years. But the problem is there's also international regulations. You're not really allowed to send somebody a reactor if they don't have a nuclear site or if they don't have the buildings or the approvals in place. So the customer needs to get the licenses from the government before we can send the reactor. And typically getting those licenses takes several years. There are some countries that are much faster than other countries. Some of the biggest countries in the world are actually some of the faster ones. The three biggest countries in nuclear energy in the world is China, India, and the USA. And those are some of the countries where it's quicker to get a license, whereas here in Europe, it takes many years to get a license. So, of course, that plays into when can we deliver? Well, when the customer is ready, more or less.
Okay, so if a customer starts working today, then we will be ready to deliver to them by the time they have a license.
Yeah, that's our expectation. I mean, there's, of course, some unknowns, but there's a high probability that we will have the reactors ready before they will have all the licenses from their government.
And then how is the business model like split between these two parties, between Copenhagen Atomics and the customers?
Yeah, so the customer is responsible for the nuclear power plant, everything. I mean, the financial cost, the licenses, the land, the neighbors, the connection to the grid, and so on. We just provide the technology. So you could say it's a little bit like Intel inside, inside your computer. There's the CPU or the chip, the main chip in the computer. In many computers, it's provided by Intel, but Intel doesn't develop the software and the computer, and they certainly don't sell it in the shops. They just provide the core technology, and it's the same with Copenhagen Atomics. We provide the reactor and the fuel is really important because that's where you have to get it right to avoid corrosion and get the price down. And that's what we have developed in the last 10 years and basically our technology platform. So that's how we provide the key technology to reach this very, very low energy cost.
And then how are we going to help the customers in reaching their licenses, both site license and construction operation license?
Yeah, so of course they need some documentation from us in order to be able to apply for licenses, so we will help them provide that. There's also several independent companies that help power plant operators to create these licenses. Some of these independent, let's call them consultants, they have had many years of experience. They've helped build some of the previous reactors, some of the light water reactors, and they've done it. So they've done it before. They have a track record of how they do it, how long it takes. But there's also some new exciting players in this game of these consultants that uses AI. And it seems that some of these new players are able to maybe make this complete package of documentation faster than what was possible before. But we also have to note that the type of documents you have to submit are a little bit different from country to country. So you cannot just make one set of documents and use that in all countries because the rules around licensing nuclear reactors are slightly different from country to country. The first thing you want to get is a site license, and we're already working with a number of potential customers to submit the first site license for commercial reactors. And we hope that one of them, or maybe hopefully several of them, will submit their site license application this year. And I think the only reason why we think that's possible is because now with AI, it's possible to generate some of these documents faster than it was before. In the old days, it was not uncommon if it was a government project, like a government wanted to build a large light water reactor, it could easily take 5 years to just generate all these documents. We hope this can become faster in the future with AI, and also with now that there's more and more companies focusing on optimizing that part of the game.
Yeah, and so you mentioned that the rules for licensing is not the same in all countries, but in general, many of the dose limits and requirements are very similar, but how you comply with those, how you prove it, can of course vary from district to district. So how similar would a license look from one country to another one? Like how much commonality is there in the documentation?
There are some countries that have similar rules, and other countries that have rules that are dissimilar. And there's also this international organization, IAEA, that tries to put out guidelines or tech documents about how all these rules and regulations around nuclear should work. Can you mention some of the typical groupings of how these licenses are similar or dissimilar between countries?
Yeah, so in a license, there are several things that you have to show. And the primary thing is to show that you meet the dose targets. So that means that if there's any kind of normal operation or accidents or severe accidents, you have to show, based on the probability, what is the amount of material that could be released. And you have to show that you meet certain levels and criteria. And those tend to be very similar around the world. And then there's additional ways in terms of how you prove that. What methods do you show that you meet these requirements? And they can vary from region to region, and there can be sort of different flavors. But overall, the basic targets that you have to meet in your design is fairly standardized across the world. And of course, they're much more strict in terms of, if we talk amount of casualties or amount of people who could potentially die, than any other industry. Now, nuclear is orders of magnitude more safe than we allow other industries to be.
Yes, I think that's important to point out that unfortunately there's sort of a lot of people out there in the world have been told by maybe traditional media that nuclear is super dangerous, and there were some big accidents in Chernobyl and Fukushima and lots of people died. It's actually not true. If you go and look at the actual data, there's only one guy who died in Fukushima from radiation, but there's many people who died from the evacuation, which was basically inflicted by the local authorities. They made some terrible mistakes after the evacuation where we ended up killing maybe 2,000 people from the evacuation. And if they've had a chance to return after, say, 1 month after the accident, then maybe only 5 people could have died from radiation. So basically, it was not because the reactor was dangerous. It was the wrong handling of the evacuation several months after the accident that killed the most people. And this is not being talked about in the media because it's, of course, unfortunate that those politicians or authorities in Japan made such a terrible mistake. And it's a culture where you don't talk about these mistakes, but then how can we fix it? And there's a little bit similar story about Chernobyl, where they knew that in order to avoid casualties, they should have given them potassium iodine pills, but they didn't do it. And then, so basically it was not the reactor that had of course there was an accident, but they could have avoided most of the casualties if the people had reacted correctly after the accident. So, and I think as a nuclear industry, we really need to learn from this, and it's super difficult because there's a lot of people keep on putting out fake information all the time, saying that nuclear is dangerous, and this brings me to the next topic, because in the U.S. there was a big debate last year, and I think it continues even this year, that in the U.S. they said, okay, these principles that the nuclear industry has talked about for now 5 decades about LNT and ALARA. We want to get away from those principles, and we want to have a science-based regulation where if we can show that people get injured, then we need to make it safer. But if we cannot show that these rules are going to save anyone, then we shouldn't have those sort of stupid rules. But maybe you can explain to the audience what is LNT and what is ALARA, and maybe why the US is leaving those principles.
Yeah, so LNT is nonlinear threshold hypothesis, talking about if you extrapolate a high dose where you do see a correlation to risk, specifically cancer, and then you extrapolate that down to 0, then there's no threshold where you can ignore it. and ALARA is as low as reasonably achievable, so trying to minimize any amount of dose, even if it's below the threshold for the given license or requirements. And in general, around the world, each country is sovereign, so it's not the IEA that imposes the rules. Each country decides, and it's in a way where most countries have decided to make those rules very strict. And in some cases, you could definitely argue that they're way too strict. But we as a company, of course, we have to abide by the rules in the countries that we apply in. But our purpose with the technology is not to try and make it even safer than the rules. We are trying to get a very low cost. So we, of course, have to see also what countries can create rules that are favorable for the reactor technology, and look at like how can we maybe start to base the licensing in a more pragmatic way where it aligns better with other industries. So, of course, if a country decides that they want nuclear to be orders of magnitude safer than other industries, then those are the rules. But there could be countries that would say that we don't want nuclear to be orders of magnitude, but just comparable safety to other industries, which, of course, becomes attractive for countries and for reactor developers to go deploy in those countries.
Yes. So, of course, like you said, if you have very strict rules, it becomes more difficult to get the licenses, and maybe you need to build in extra safety systems or whatever. But is it fair to say that if you take a country with a light set of rules and compare it to a country with some really difficult rules, that the cost of that electricity could be 2 or 3 times higher in the country with the difficult rules?
For sure. Like having stricter rules is kind of taking an insurance in the requirements in the law. And the more insurance you want, the more expensive it becomes. So if you want to make nuclear infinitely safe, it becomes infinitely expensive. And there's, of course, some correlation between the amount of safety that you require from the plant and the cost of it. And all those safety systems adds up. All the licensing and documentation adds up. So it's really for countries to decide what level of safety do they demand from their nuclear.
Is it fair to say that if you look at the whole world, then, of course, we get most of the electricity in the whole world from natural gas and coal today, and there's 31 countries that have nuclear energy today, and that means there's another 160 countries that do not have nuclear energy. Is it fair to say that most of those countries chose not to have nuclear energy because it is expensive, and they prefer to use natural gas or coal because it's cheaper, and they didn't mind that coal, for example, kills 1,000 times more people per terawatt hour of energy produced than nuclear? But it was basically those 160 countries decided to choose and use coal because it's cheaper.
Yeah, you could definitely postulate that was their motivation to do so. Coal kills passively a lot of people, but it doesn't have the same potential to have severe accidents that could kill a lot of people. So the risk profile is different from nuclear to coal. But for sure, coal kills many, many more people than nuclear probably could ever do.
Yeah, you're correct that coal is it kills people slowly because of air pollution and dust and so on. And actually, when you run a coal-fired power plant, the ashes that are left behind, they have uranium and thorium inside those ashes, and that becomes a waste product. And normally it's used for road fill or something like that, or used in concrete. But you could actually take that ashes and extract the uranium and thorium, and then generate 13 times more energy from those ashes than what the coal generated when you burn the coal. So that's a little bit of a fun story, but we don't do that anywhere in the world. They just basically throw it away. But that tells you that it's radioactive. It kills a lot of people, like 1,000 times more people than reactors would have, even the worst type of reactors like Chernobyl. But it also tells you that most countries actually prefer to use coal because it's quicker to build, and it's less expensive, or at least in most countries it was less expensive. But how do you think it will change now that we say that Copenhagen Atomics is coming with a new type of reactor and a new type of fuel, that suddenly we can deploy it as fast, or in some cases even faster than coal-fired power plants, and also the cost will be lower than electricity from coal, and it will be much safer because it will be just as safe as the other nuclear power plants. So do you think there's 100 countries who want this technology right away, or how do you think?
There's definitely the opportunity for any country to deploy this technology at a massive scale. So part of what makes the way we build it very attractive is that we can actually scale and mass produce these reactors, and we're not limited by enrichment supply chain. We can basically build and deploy as many as reactors as feasibly possible. And this basically means that any country can choose to take a huge portion of those reactors. And you might think that, okay, but a country only needs so much electricity. But when the price of the energy becomes this low, you can also start to make commodities like ammonia, steel, aluminium. And when you make commodities, the value of those commodities is much higher than the cost of shipping it. So that means that basically any country can, in a very small amount of land area, produce a huge amount of energy. And even a small country could easily deploy a terawatt. That's like a significant fraction, like 5% of global energy today, in just one country, produce commodities and then sell them around the world. So this is not limited for giant countries to deploy. It's basically the opportunity is there for any country to make this a technology that can be licensed and deployed fast.
Yeah, and this is one of the things that I find super exciting. This is also sort of one of the main reasons I got involved in this technology, because I realized that suddenly you don't have to be a big country to get access to this technology, and suddenly it really changes the game in the whole world, because before we have had many wars and there's a lot of geopolitics around oil and gas, because it's a scarce resource and it's used by every country in the whole world, and it's having access to coal and oil and gas is very clearly linked to all the major commodities that we need. So steel, aluminum, copper, cement, ammonia. Ammonia is a fertilizer used for making almost all the food in the world. So those commodities are super important in geopolitical terms. And suddenly we change the whole game. Like all the rules that we knew for the last 50 years are sort of suddenly out with the bathwater, because now any small country can make half of all the steel in the whole world. And this is definitely going to be a game changer. It's most likely that any fast reactor will be more expensive than a light water reactor.
You can definitely get the price of manufacturing the reactors down, but you have some physical constraints on how small you can make a critical assembly.
I believe when we get to year 2100, half of all energy in the entire world will come from thorium. And today we get no energy from thorium anywhere in the world.
You can easily make a very small reactor that can run on one fuel load for 20 or 50 years, but that basically means that it's not utilizing its potential. It's like driving a Ferrari around in a parking lot, its whole design life.